Hello. In this module, we will be talking about the concepts of skewness and kurtosis. Though we have already talked about them in previous modules in different contexts, but in this module, we'll be talking about their measurements and making decisions based upon them. Since we already know that our distributions can take three different types of shapes. It could be symmetric, that's pretty much bell-shaped. It could be positively skewed, which is also right-tailed, and it could be negatively skewed, which is left-tailed. In symmetric distribution, mean, median, mode, all three are equal. Whereas in positively skewed distribution, mean is going to be the largest value as compared with median, and mean both are greater than mode. And for negatively skewed data, mean is going to be the smallest value. Then it comes the median, and then it's the mode. We can also make these comparisons by just looking at the mean, median, and mode values. That if we find that all three different measures of central tendency are equal, we define that our variable has a symmetric distribution. And similar way, we can make decisions using these different central measures of central tendency regarding the skewness of the data. Skewness is known as the departure of symmetry, and the measures that help us to identify and measure the amount of this departure from the symmetry are called the measures of skewness. It is in general denoted by SK. This idea was given by Carl Pearson when he talked about skewness as a ratio of mean minus mode with the standard deviation. In many of the datas, mode is not unique value. In such situations, we use a different relationship that defines mean, median, and mode, and this is that mode equals 3 times minus twice the mean of the distribution. This relationship is true when the distribution is moderately skewed. Hence, using this relationship in the previous formula for the skewness, this formula for skewness, for the coefficient of skewness, can be modified by 3 times mean minus median divided by the standard deviation. Later on, A.L. Bowley gave another formula for the skewness, which is based upon quantiles, where it used a first quartile, third quartile, and second quartile, that's median, and its ratio by the interquartile range. Let's take an example for GRF measurements to see that how do we think about while we make decision using different measures regarding the skewness of the data. The very first measure that we use to observe the shape of the distribution is the histogram. From this histogram, we can see there is some extreme observations on the left tail. And if we draw a frequency curve upon it, and frequency curve is a freehand curve, this clearly shows that this is a negatively skewed distribution. Moreover, if we look at the mean and median for this distribution, we can see that median is greater than the mean. And this is something that's true for the negatively skewed distributions. Since in this data there is no most frequent observation, since all the observations are just once, therefore there is no mode in this data. So when there is no mode, we can also make comparison of just mean and median to make the decision out of it. Moreover, due to the absence of mode, we cannot use the formula that requires mode into it to measure the coefficient of skewness. Therefore, we'll use the one that uses this empirical relationship between three different measures of central tendency. Here for this data, if we can see the mean GRF is 30.58, then we have this median GRF, which is 31.10, and the standard deviation is 6.03 newtons. Substituting all these values into the formula for the coefficient of skewness, the value turned out to be minus 0.259. For these coefficient of skewness, there are different ways we can make decisions. Like if the coefficient of skewness is equals to 0, we call our data to be symmetric. If the value of the coefficient of skewness is greater than 0, we call the data to be positively skewed. And if the value of the coefficient of skewness is less than 0, we call it negatively skewed. In our current example, the value of the coefficient of skewness turned out to be minus 0.259, which is less than 0. Therefore, it recommends that it is negatively skewed data. Similarly, we can use the A.L.Bowley's method to measure the coefficient of skewness. Here, we have the values of Q1, which is 27.25. We have the value of Q2, which is 31.10 newtons, and value of Q3. Here, the value of Q1 is a point that has 25% observations below it. Q2 is a point that has 50% observations below it. And Q3 is a value that has 75% observations below it. If we use this information into the coefficient of skewness that was given by Bowley, it turned out to be minus 0.23, which also refers that this coefficient of skewness is less than 0, which means that the distribution of our variable is negatively skewed. For the measures of skewness, we do not calculate any measure of skewness for qualitative variables. But for quantitative variables, we use different measures like frequency histogram, frequency curve. We also use to compare mean, median, and mode. And finally, we use coefficient of skewness. The other measure is kurtosis. Kurtosis help us to measure the peakness of the data. There are three types of peaks. It's leptokurtic, it could be mesokurtic, or it could be platykurtic. There are two different formulas that could be used to measure the kurtosis. The first one is based upon moments, and the second one is based upon, again, the quantiles. In the moment formula, if the value of Ku is equals to 0, the distribution will be called mesokurtic. And if the value of the Ku, which is the coefficient of kurtosis, is greater than 0, it will be called leptokurtic. And if the coefficient of kurtosis has a value that's less than 0, it will be platykurtic. But if we use the formula that's based upon quantiles, over here, the K ranges from 0 to 0.5. And if the K is equals to 0.263, it will be mesokurtic. And if the K is greater than 0.263, it will be leptokurtic. And finally, if K is less than 0.263, it will be platykurtic. For our example of GRF measurements, if we use the moment formula, the value of the kurtosis turned out to be 1.45, which shows that this distribution is leptokurtic. Moreover, I'll leave the calculation for the coefficient of kurtosis using this quantile formula on the readers. There is another example where mean, median, and mode for all leptokurtic, mesokurtic, and platykurtic distributions are equal, with different coefficient of skewnesses. Here we can see that even if these different measures are equal, but the distributions have different shapes. They could be mesokurtic or they could be skewed. They could be leptokurtic, they could be skewed. And they could be platykurtic and they could be skewed. But there's one ideal situation when the distribution is mesokurtic as well as it is symmetric. This indicates that our distribution follows the normal distribution, which is one of the very desired properties in many of the statistical methods. While conducting the data analysis, we do not rely only on one measure of skewness. We use graphical methods, we use different numerical methods. While we use numerical method, we first observe them with the comparison of mean, median, and mode. And then we also calculate different measures of skewness. Manual calculations using the formula for the kurtosis are sometimes not feasible, but there are a lot of different statistical packages which help us to calculate these values. Thank you.